Thank you very much, Avi. Appreciate that introduction. You are free to leave.
Thanks, my friend.
Hey, no, thanks, Avi, and have a good rest of the day. All right, folks, you're stuck with me. I'll carry on with the webinar today. Thank you so much to everybody who's joining in. You are the few who made it through all of our filters. You may have noticed we moved the day at the last minute. We locked the registration by accident up until this morning. I really feel like we were just trying to limit the number of people here today. So to the 16 or 15 or so people who were joined today, thank you very much for your tenacity in getting through our filters. We appreciate you joining us today. All right, which is good. Small groups are good. If people have questions or they want to do discussions and so forth, it does give us better opportunity to do that. So I don't mind small groups at all. That's fun. I always teach big groups and big classes, so this is fun. All right, so what am I going to do? I'm going to do a really quick introduction. I promise I'll be quick. I'll give the goals of what we're going to cover. You know, just by, give me a show of hands. Is everybody able to see my slides? Put your hand up if you can see the slides. All right. Thank you very much. I appreciate that, you all, for interacting with me. Now, if you have a question, feel free to use the chat window. I'll be watching the chat window. You see that Avi already put a contact for himself. If you're having a technical difficulty, please email him. He can respond very quickly. We'll help you if you're having something technical come up. Okay, then I'll talk about the goals. Now, everything else, artificial neural networks. You see the common denominator here, the motivation, the architecture, how do we train them, i.e. backpropagation, stochastic gradient descent. We'll talk about that very quickly. Designing them, very cursory. We'll just talk about some considerations in designing them. We can't cover the depth that I would like to cover during a hour-long webinar. And then we'll do a demonstration in Python using TensorFlow. Okay, and so we'll show you how to build the world's simplest artificial neural net, and we'll change it up and show you how we can modify it. Let's do a quick introduction. Anybody here, if you've never met me in person or heard me speak before and you saw my name and you thought, what? There's no vowels even? That is pronounced Pyrcz. That's the way we pronounce it from my family's 100 years in Canada, away from the Ukraine. I think we forgot how to pronounce it. But anyway, Pyrcz is the way we do it. I'm from industry. I started as a professor just in 2017, 13 years of experience. Everything I teach and talk about, I've done in practice. So I speak from experience. I used to lead a large research program. I was a team leader. I used to review projects all over the world, and I still do a lot of teaching in industry. I'm very flexible. If anybody has an idea, anybody has something they want to bring up, we can talk about it. During the regular courses, we have tons of opportunity to go into deeper dives. I have a lot of course content. I'm available. I have an open door policy. Students drop in all the time with questions. They email me and so forth. I'm an engineer and a geoscientist. If I speak like an engineer and you're a geoscientist, show of hands, who here today is a geoscientist? I'm curious. All right. I see one. Is it really just one geoscientist? Interesting. Okay, two. He was right. I saw that. You get full marks for that. Oh, and that was quick. That was a hand up and down. People are a bit shy about being a geoscientist. Show of hands. Who's an engineer? Who's our engineers? Mir, Hasheng, Gaia. I see a bunch. Wait a minute. There's people who haven't voted. Is there anybody here who's a data scientist, hardcore data scientist? Not an engineer, not a geoscientist, came from the data science route. Mathematics, statistics, coding, computer science. No, I don't see that. Finance? HES? Other? Okay, curious. Okay, but if you're an engineer and I speak like a geoscientist, I can switch. I'm bilingual. I can speak either way to help make this make sense to you. All right, and I often teach. I teach many groups. I've produced a lot of content in the topic, and I'm always happy to discuss. Aside from Datum, I do post a lot on YouTube. All of my lectures from the University of Texas at Austin are available on my YouTube channel. Anybody here watch my YouTube videos? Anybody seen them? Renato, I saw that. Whoa, Ben, everybody. Okay, Fabio, thank you very much. Okay, good to hear. I hope the content is useful to you. Thank you very much for that. I put a lot on GitHub too. I have a lot of content. I want to support working professionals and students. What's the goal today? Let's cover the very basics. Theory, I would say it's more kind of nuts and bolts and an application so you can use it immediately. Artificial neural networks, how do you get it done? I want to strengthen your machine learning knowledge through accessible content. Now, everything we do, we try to build on a foundation of statistics, the theory, examples, well-documented examples to get you started. That's my goal. What's the motivation for artificial neural networks? I love this stuff. I really do. This is the part of modeling that's known as natural computing. And it's the idea is we look to nature for inspiration. The way to think about it is this. Our environment, our world has had 4-point-something billion years to build good systems. So we look to those systems as very useful to solve problems. That's what it's been doing through, I don't know, I'm not a biologist, okay? But we can look for natural examples that we can use to solve problems. Artificial neural networks are inspired by biological neural networks, specifically of higher order like mammals. That's my understanding. The nodes in our model are artificial neurons. The connections are artificial synapses. Now, I've been told by this wiki journal of medicine that this is what it looks like. And don't ask me anything about it. It's all just, I have no idea. But you can imagine there's a biological system that does this. Intelligence emerges from many, many interconnected processors. How many? I understand it's trillions. That's what I heard. The result is it becomes a universal function approximator, which is a fancy phrase that means our resulting model that mimics this natural setting can reproduce any natural setting, any complicated function, as long as it's sufficiently complicated, enough nodes and connections. Okay. All right, let's go ahead and talk about artificial neural networks. Now we'll give the prerequisites, the basics. Artificial neural networks are a form of supervised learning. What does that mean? It's all about building a predictive model. So every time somebody says artificial neural networks, please think of this function right here. You've got inputs. They're called the predictor features. Those are the inputs, X1 through XM. You've got output or outputs. Those are the response features. You've got a function that takes you from inputs to outputs, and you acknowledge that your model will have error. That's the error term there. That's it. And I'll tell you what, if you've done machine learning before, linear regression, the same thing, or if you're doing support vector machines or whatever else you're doing, random forest, it's the same formulation, okay? This is predictive machine learning, supervised because we provide it with training data for which you know the answer, and you're going to train it to do a better job giving you back the answer in training, and hope and test its ability in testing with data not used to build the model. It's nonlinear. The ability to predict complicated interactions between the predictor and predictors and response features is critical. And you'll see we can produce nonlinear models all day long. It can do that. Let's talk about the architecture of an artificial neural network now. Very straightforward. This is our new friend. This is our very simple artificial neural net. I will use it for all of my descriptions right now. Okay, it is not a fancy artificial neural net. It has a single hidden layer. I will define that shortly. It's feed forward. All of the information goes from the predictor features through the network to the response feature or features. Feed forward, all information is going through, fully connected. All of these nodes are connected to all of the nodes in the next layer. Not a big deal. Okay, so let's walk through it. Let's talk about the parts. The connections, whatever this node does, it will give, whatever its output is, will go to all of the nodes in the next layer. Those are connections. Now they're moving in which direction? I always forget which way I'm going to show up, but from left to right on your monitor on this figure. Okay, so whatever's the output here will go to all of the nodes in the hidden layer. And whatever comes from this node in the hidden layer will go to all nodes in the output layer. These connections, if you look, we have the full combinatorial 1, 2, 3, and whatever number M is, 1 through M, 1 through M, 1 through M connections. Everybody's connected. And feed forward, everything in the connections is going that direction. Now, you might wonder, do we ever not do that? Well, yeah, there are networks that actually allow things to come back. Recurrent neural nets are an example of that. We'll mention it later, but we won't go into that detail today. Let's talk about the nodes. The nodes are really a modified form of linear regression. They're really simple. They're a simple processor. They're going to take linear weighting of all the information from the previous layer nodes. They can combine them by linear weighting, just like linear regression. They'll even add a constant term, which we'll call a bias term. And then we're going to apply a nonlinear transformation to the result, and we feed that to the next layer. We'll talk about the details, but that's what the nodes are. They're like tiny little simple processors. And that's what happens in your brain. It's incredible. It's really, really neat. Through many interconnected nodes, you get very flexible predictions, emergent ability to characterize very complicated nonlinear patterns like we do. We can see very complicated things, in fact, understand them. Now let's define the layers. Remember, I've got a single hidden layer. Okay, there's my hidden layer. How do we know it's a hidden layer? It's tucked in, it's sandwiched in between layers. It's never exposed to the outside of the network, not the front, not the back, okay? So we got an input layer, that's where we're gonna have the predictor features feed into it. And we got the output layer, and that's the outputs to go to the response feature or features. Deep learning, if you ever heard that definition or that term, is in fact just the use of artificial neural nets for which we have more than one hidden layer. In fact, we'll do it today. We'll add a hidden layer, and then we'll say, look, we did deep learning. Now, I want to acknowledge that things get much more complicated, and people build very complicated types of configurations, convolutional neural nets, recurrent neural nets, and then there's very complicated architectures in which multiple networks are working with each other. It gets very, very interesting. So I don't want to trivialize the idea of deep learning, but that is the threshold. Now let's talk about the overall, what are we going to do as far as normalization? Feature transformations. It turns out if we have X1 through XP, or the inputs for our network, those are our features, our input features. And like we could be predicting production. This could be porosity, this could be saturation, this could be permeability, or maybe these are different mineral grades and we're trying to predict the mill efficiency or recovery factor from the mill. You see what I'm saying? Well, we're going to do a normalization. Why do we do normalization? Well, we had to do normalization in many machine learning methods. It's really important in order to improve performance of the prediction. Now, what is normalization? We're going to transform the features to a specific range. It's very simple. Min-max normalization from -1 to 1. By doing that, we center it on 0. We remove the differences in scale or degree of variance or magnitude between the features, which could kind of bias and alter our model. But most importantly, we're going to improve activation function sensitivity. It turns out these nonlinear transforms are kind of centered on 0 and have certain ranges over which they're sensitive. It's improved by normalizing. Min-max normalization, -1 to +1. Now, it turns out we're going to probably also do a reverse normalization of sorts, and that will be to get from some transformed output to what we really want to predict. Okay, it's the same problem. We don't want to have crazy units that are going to have a huge impact on the network and decrease its sensitivity. Predictions are in normalized response features that are then going to be back transformed. Okay, now let's go ahead and walk through our artificial neural network from step to step. Okay, so we're going to start, we do a normalization. We took our predictor features, they're normalized. We're now at these nodes right here. Now let's go to those nodes and we're going to step through to one of the hidden layer nodes. The way we're going to do that is we're going to go ahead and calculate a set of weights for all of these inputs from all of those nodes. We're going to calculate a bias term. The weights and the bias term shown here are model parameters for our artificial neural net. And if you look at it, it looks just like linear regression. We're going to apply a nonlinear transform to it, and that's going to be the activation function. Okay, so this is what's going on inside of the node. That's all of the details. Now, one little detail. Usually you'll have separate bias terms for each one of these nodes. You can use an architecture where all of the nodes share the same constant bias term. You can do that too. The intercept in like a linear regression problem, right? Okay. The thing we're going to do then is once we calculated that, we're going to apply an activation function. Now, the activation function is going to go ahead and it's applied to the linear combination plus the bias term, and it's going to be a nonlinear transformation that's critical for this system. And I'll talk more about activation, but spoiler alert, it prevents the system from collapsing to just really a very verbose way to do linear regression. By doing these stepped activations over each one of the nodes, it prevents the system from collapsing and simplifying to just this very simple linear regression approach. Now what we do, whatever we get after the activation, we pass to all of the nodes in the next layer. Now for our simple single hidden layer, the next layer is the output layer. We got 1 through K output nodes right here. Whatever information we have is going to be passed. It's the same information. From this node, the same thing goes to each one of the nodes. It's not going to be different. Then at the output node, you notice the symmetry now. We're going to do the same thing. You see, we're doing a linear weighting of the inputs from the hidden layer nodes, and we're going to do a activation function. Now, this is interesting. If we're doing simple regression, in other words, the output here should be something like a continuous value. In that case, typically we use an activation function known as linear or identity. Now, I like saying identity because look at it. It's very simple. Whatever the function is, t is going to be equal to t. In other words, it's no transformation at all. Okay, identity. Now, if you're doing classification, we'll use this right here. It's softmax activation function. Now, if you look at it, what all it's doing is very simple. The exponentiation of the result from this calculation results in a measure that will always be greater than or equal to 0. It forces it not to have negative values. And in addition to that, by standardizing by the summation of all of the values from those calculations over all of these nodes, it forces them to sum to 1. Okay, greater than non-negative sum to 1. Well, it sounds like Kolmogorov talking about axioms of probability. That's all it is. It's just ensuring that these are probabilities. In other words, node 1, node 2, node 3, those will sum to 1 and have non-negative. Those are now probabilities of 3 categories. That is a classification output. Okay, I hope that's helpful to all y'all as far as a walkthrough of what we're doing. You're dealing with a regression problem. No, you can reverse transform it to get it back into the units of porosity with its specific distribution. That might have been difficult to work with otherwise. Okay, so we do our back transformation. That's it. Now, when we're going to train our artificial neural network, I want to convince you that there's a lot of work to do. It's going to be a huge number of parameters. In fact, for every connection, there is going to be a weight. And if you think about it, for a fully connected feed-forward network, that's going to be P input layer times M hidden layer, that product. That's the number of weights we need for all of those fully connected, the combinatorial. And then from going from the hidden layer to the output layer, we have M nodes in the hidden layer to K nodes in the output layer, that product. And then at every single node in the hidden layer and the output layer, we have a constant term. So we have to increase it by this. In other words, the number of parameters that we need to train is this equation right here, where P is the number of nodes in the hidden layer, I mean, in the input layer, M number of nodes in the hidden layer, K number of nodes in the output layer. So this is going to add up very quickly. I will show you, we'll build a simple artificial neural net. We're going to have like 50,000 parameters. We can get there very, very easily just by adding a few additional layers and making them very wide. Lots of nodes, we'll get there. Okay, so we got a lot of work to train them. Now, let me just make a comment about activation function. Now, it is a nonlinear transformation of whatever we got from that linear combination plus the bias term inside of the node. It introduces nonlinear properties to the network. The way to think about it is, if we didn't do that, we could take that entire network and collapse it down to a linear system. By using the activation function and carefully selecting one, we increase our power and efficiency to learn complicated patterns. That's what it's all about. Now, I feel like I'm creating suspense. Let me jump ahead one slide. What does an activation function look like since it's so great? Look at it. This is it. These are nonlinear transformations. Here's the logistic. Here's the equation. Very simple, very straightforward. The input comes in, and this is the output right here. Logistic results in values that are going to be between 0 and 1. Tan H is shown right here. This is going to result in values that are between -1 and 1. You can see the input here is centered on 0 right there. And ReLU, which is very popular, used commonly in convolutional neural nets, that one actually has a step. It's going to be constant if you're below 0, and it goes up linearly. In fact, it's identity if you're going to be greater than 0. And so it turns out that all of these functions, I hope I can convince you, impose nonlinearity. Anybody who works in linear systems and so forth will recognize as soon as you apply this function, oh boy, now things are more complicated. Okay, given you now have seen the images and I've demystified or at least spoiled the excitement over what activation functions are, let me just make a couple of comments about how you choose them. Now, first of all, nonlinearity is going to be essential. In fact, the universal function approximator proof is based on work back in 1989, and it required a nonlinear transfer function. So if you want to go back to a nonlinear activation function, if you want to read about that, you can go back to the original work there. It turns out that continuously differentiable, which you saw in all of the cases except for ReLU, is really required for stable gradient-based optimization. And there's a bunch of kind of comments or further details we can go into there. It turns out that approximates with identity at the origin, well, they'll learn efficiently with weights initialized to small random values, which is really useful as we start out our neural net. We know we can just use small random values, maybe Gaussian distributed with a small dispersion, and we're good to go get started. So there's all kinds of issues around choosing activation. We'll just demonstrate doing things with ReLU, but we can switch it up when we do our demonstration. And there's more details we could cover. Let me give you an overfit warning. We did a hackathon at our department for the entire University of Texas at Austin. My co-host of the hackathon was Dr. John Foster. It was great, 100 students, 21 teams. And I'll tell you what, the winning team did linear regression. I believe it was ridge regression with a hyperparameter. Simplest model you can imagine. Artificial neural nets tend to be highly complicated. They tend to have a lot of parameters. It's a non-parametric model, but the actual model parameters can be huge. Fitting, if we do that, work with complicated models, there's always a risk that we are pushing ourselves to high model complexity. We're going to have low error in training. And if we do fair testing, we will see higher testing error. If we're in that zone of high testing error or increasing testing error and decreasing training error, we are surely overfit. This happens all the time. People overfit these models for sure. Well, so we have other lectures where we talk about the variance bias trade-off and overfit and how do we test and how do we do fair test. Please be careful with these methods. Don't build models like this. This is an overfit decision tree where you got zero error at the data, zero ability to predict away from the data. Okay, let's go ahead. That was a safety moment with Dr. Pyrcz, I guess. That would sound kind of, I hope it doesn't sound grumpy at least. Okay, training artificial neural networks. How do we do it? Okay, what are we going to do? Recall the model parameters are the connection weights in the node bias terms. And you remember I showed you the equation where we can calculate the number of parameters. It's going to be pretty big. Set the neural net parameters, model parameters, to random values, Gaussian distributed small dispersions or variances. You do a forward pass of the model. Now you might be thinking to yourself, what? You're going to do a forward pass with random parameters? How's it going to predict? And the answer is, it won't. It's going to be terrible. It's going to have a lot of error. Okay, that's fine. Because then what we're going to do is we can go ahead and we can calculate the error in these predictions. That's what we're going to do. Okay, so let's talk about how we're going to do that. We're going to go ahead and define a loss function. Because I don't care about the error at one training data location. I need a norm. I need a summarization over the error vector. So we're going to get a single value to summarize the mismatch over all the training data. Very common thing to do is an L2 norm. This is an L2 loss right here. It's simply taking the predictions we had versus the true values. Remember, this is supervised training. We know the truth at the training data. We're going to square it, summarize it, or sum it of the squares over all of the training data. That's our L2 loss. That's our P. That's going to be our overall performance of our model. Now what we could do is, now you could do a variety of different methodologies for this. You could go ahead and you don't have to do the sum of the squares. You could do the average. If you think about it, that's just applying a constant. That doesn't really make much difference. And people do consider other norms, but there's all kinds of issues around norm choice. Don't have time to get into that today, like an L1 norm and so forth. We can calculate the partial derivatives for the performance given each weight. Now let's look at this. This, remember, P is the norm, the summarization of the error over all of our training data. It's literally going to be a single value. This right here is the weight at the P location for the connection between the P input layer node and the M hidden layer node. That is literally one parameter in our model, right? And so we can calculate the partial derivative. The partial derivative is going to be awesome. It's going to show us how does the error change in our model as we change that one parameter. Now, can we all agree, if I could calculate that for every one of the parameters of my machine, I would know the direction that I should change it and how fast I should change it. If it's got a huge impact in the error, I might want to make a smaller change. If it's got a small impact, maybe I need to make a bigger change. And if it's a negative impact, maybe I'm going to want to decrease it. You see, it's kind of, we can move it in the direction to improve the performance, or to maximize, well, in fact, to minimize P, our measure of error. Now what we do is, since this is the gradient, we need to move the weight or the parameter. We can now decide on a learning rate to control it. We don't want to just let it go and perfectly fix it. We want to go to the answer slowly. So we'll set an R constant, which is the rate at which we learn. So we got the gradient here, we should move it. And then we have the rate we want to go at to basically control it. And then this is the change to the model parameter. Okay, so we can do that over all of our training data. Now, how are we going to do it? Training is iterative. What we'll do is we'll have epochs. I love it. Machine learning folks take terms from all different sciences, and I think they pick the terms that sound the coolest: epochs, inertia, whatever it might be. Epoch is going to be one cycle over all of the training data. Okay, now it's going to go by batches. A batch, you're going to randomly select a subset of the training data. You're going to calculate the model. Then you use partial derivatives and the chain rule, won't go into details today, to do back propagation. Back propagation is the assignment or allocation of the partial derivative, the change in error versus the change in the parameter back through the system. It's very efficient. It can be done very efficiently using GPUs and so forth. And then what we do is, because we took a subset of the data, a batch, Well, we have to loop over all of the data to do an epoch. So if we took a fifth of the data, we have to do 5 batches before we get done with our epoch. But every time we do a batch, we'll do an update to the model parameters. Okay, let me make a comment here. Larger batches result in a better estimate of the error. I hope you can see that. If you use all the data, the training data, you have the best possible estimate of the error. But it'll be slower on the individual epochs because you had to do, it takes longer to do that one batch. Smaller batches result in a noisier estimate of the error. But guess what? That stochasticity is powerful. It's very useful for optimization, i.e. stochastic gradient descent. And that's what we're doing here. But faster epochs often result in faster learning or even possibly more robust models. So we don't tend to use all the data in a batch. We usually subset the stochasticity, and the very fast iterations usually result in a very good solution. Here's what it looks like graphically. We're going to go ahead, we take our network. Imagine that we have initialized all of the parameters of the network with random values centered on 0, small dispersions or variances, okay? Now we go ahead and we take the training data, we're going to apply it for a single batch, a subset of the training data. We calculate the estimates. We take the estimates and we calculate the norm. We now have a summary of the error. By using the chain rule and partial derivatives, we can back propagate through the network and we find out how does changing each one of the model parameters change that error. We then can apply a learning rate and this gradient to know how we should change or delta each one of the model parameters to improve the estimate, i.e. minimize the error. Okay, then we go ahead, select a new batch, and we go again. That's what we're going to do. Okay, I got a question. Can we use batch training as some sort of ensemble learning? I mean, if we assume representative sample in each batch, is it possible to do something like bootstrap? Oh, I love it. I love it. So let me make a comment. And there is a bit of a push-pull when it comes to machine learning and bootstrapping. Let's think about, if I may, and Fabio, thank you very much for the question. Great question. Let me go ahead. I think I can just do it like that. If everyone can see the question, I hope that helps you now. Okay, Fabio, so if you think about bagging, the whole idea of bagging in machine learning is you get ensemble estimates, and we use that to dampen model variance by taking the average of the estimates. Okay, so in that case, bagging or bootstrap of the data set is used in order to improve the accuracy by reducing model variance. Okay. Now, in other cases, there are cases in which people will do exactly what you said. We'll say, oh, that's a realization. And then they'll use it as a methodology to get an ensemble for the purpose of representing uncertainty. Okay. Now, let me just make a comment. I want to drive this a little further if I can, and I hope not off the rails. An excellent example in deep learning and convolutional neural nets specifically is what they call dropout, where what you do is you randomly remove some of the connections. When they do that, you actually get different estimates. Now, when they do dropout, what they're trying to do is they're trying to add more stochasticity to the model predictions to improve stability. But because artificial neural nets take too long to calculate, we can't really spend the time calculating a bunch of models. Instead, we put that randomness directly into the model. Okay, so I hope that this is helpful to you, a general discussion around the use of bootstrap to improve model accuracy and perhaps even give you uncertain models. I have a PhD student. We have a paper that just came out in the Journal of Petroleum Sciences, where we actually demonstrate using dropout to get realizations and represent uncertainty in deep learning. Okay, let me just do a really quick summary right now. And I think this is really important. I mentioned backpropagation. People often mix this up. They think backpropagation is the way that artificial neural networks are solved. It turns out backpropagation is just the calculation of the artificial neural network model parameters training error partial derivatives. That's taking the error and propagating it backwards through the system to find out to what degree does the error change if I change each of the model parameters. Okay, now the stochastic gradient descent is an optimization algorithm to minimize the loss, RP, error over the training set, and it has aspects. Stochastic, the use of random batches. You notice we're doing that, and this gets at Fabio's question. Using random batches induces stochasticity, randomness into the error calculation. It becomes stochastic in its descent, and it's gradient descent because we use the partial derivatives to figure out the gradients and a learning rate to go downhill, to go down to a minimum value for loss. Okay, so the way to talk about artificial neural network training: cycles through batches of backpropagation and stochastic gradient descent steps. Okay, and so if you know optimization and you think about learning rates and you think about momentum and you think, hey, I'll tell you what, all of that optimization knowledge you have, boom, you can use it right now. You could understand ADAM, which is a very popular optimizer in artificial neural nets in TensorFlow. It's available and it's adaptive. It uses kind of the variation observed over the training in order to decide how big the step should be. This stuff is super cool. Okay, there's tons more we could talk about in optimization theory. Okay, let's just make a very general comment about learning rate. Remember the R right here, we got the gradients. We know we want to change in a certain direction each one of the model parameters from these partial derivatives. Now we're going to restrict it with a learning rate. The R hyperparameter controls the rate of weight updating in response to the gradient that we get every time we do a batch cycle. Low learning rate, well, think about it, will become more stable, but slower solutions, and perhaps if you think about stochastic gradient descent, can get stuck in a local minimum. It doesn't have the ability to search the solution space, perhaps. High learning rate, faster solution, perhaps, maybe not. It may be unstable, maybe diverge from the optimum global minimum. And you can do things like learning rate decay. These are other things we do where over steps, you kind of slow down the learning so we don't just keep oscillating around. Okay, there's a lot we can do. There's momentum. Oh, I should have a figure for this. If I go in a certain direction for one step, I don't want to come back right on myself for the next step. That's oscillation, that's instability. A momentum term says the next step, in other words, the next change to any one of the model parameters is going to be a function of the previous change weighted and the remainder of the weight being applied to the next update. In other words, momentum. If I went this direction, the next time I make a change, I can maybe go like that, but I'm not going to come right back on myself. I'll kind of move in a smooth manner as without oscillating through the solution space. Okay, which is very cool. Very cool. I made an animation. I'll tell you what, tomorrow I'll put that animation on Twitter of a stochastic gradient descent display animated using Matplotlib and Python. It looks so cool. You can set the parameters and see what it does. It's very cool. Let's just talk a little bit about designing artificial neural networks. And I should get right to showing you one. I'm going to run out of time if I don't. Hyperparameters. Well, yeah, there's a lot of various parameters that are really related to how do we optimize and find the best solution to minimize the error. Learning rate, as I mentioned, there's some tradecraft as far as how we set it. Momentum is another term we can use. The performance metric, is it L2, L1? What are you doing? The width of the artificial neural net. Now, this gets us into solid hyperparameters as far as constraining the complexity of the system. The number of nodes in each layer. When I drew the artificial neural net lying on its side from input to output, the width is in this direction. The depth is the number of hidden layers. You need input and output layers. You can't do without them. But do you have one hidden layer, 2, 3, and so forth? The activation functions, that's also an important choice. I mentioned a couple of criteria for choosing them. There's a lot more details. And the output function, the activation function is usually going to be given by the type of problem you're working with. Now, let me make a couple of comments on limitations. Anybody here ever heard of the no free lunch doctrine or theorem? I did a PhD. I spent my whole time, hey, thank you. Renato, I saw other people. Thank you for putting your hands up on hearing about the no free lunch theorem. I was a PhD student. I'll tell you what, I learned that there was free lunch. I spent a lot of time as a PhD student finding free lunch. cannot guarantee the model is always optimum for predicting new unobserved cases. Anybody here a fan of the black swans, or read about or learned about black swans? That's the idea right there. You study white swans your whole life, you would never be able to predict black swan occurring, right? Parameter rich requires a large number of training data. There is a trade-off. In your head, when you do machine learning, do not let go of your statistics knowledge. Remember degrees of freedom. Degrees of freedom are equal to the number of pieces, independent information minus the number of assumptions, parameters for the model. If you're negative degrees of freedom, be worried, right? So we know that, right? Be very careful. Low interpretability, generally difficult to interpret the models. I have a lecture on model interpretability and Shapley values and other methods. High complexity model, high model variance, and perhaps we may be overfit. Okay, there's a whole variety of different types of artificial neural network designs you can work with. Deep learning. Go beyond one single hidden layer, more complicated. Recurrent neural networks, information that can flow backwards. I have lectures on convolutional neural networks. Image data, 2D, model data, 3D, fantastic. It's actually an adjustment of the artificial neural network, which is really cool. It's actually a form of regularization in which we make the artificial neural network work with image information the way our visual cortex does, which is, once again, natural computing again. Autoencoder, this stuff is mysterious. I'm just kidding. Really, really cool. Dimensionality reduction types of approaches. The network gets narrower and then it gets wider again, which is super, super cool. Okay, let's go ahead and do some demonstrations. I'm going to open up one and demonstrate it, but we have a whole bunch of other demonstrations, like some really tricky ones like this one right here. It's kind of cloudy. It's very difficult to work with and demonstrate, so if you want, there's multiple demonstrations. There's convolutional neural nets. This example was used to build a predicted porosity map from a available acoustic impedance map with noise. It's pretty noisy. And that example is available, but I want to go ahead and show this other very simple example. Where do I have it? Here it is. Okay. Show of hands. Can you all see my code? All right, Renato, Julio, I appreciate. Nusrat, thanks a lot, folks, for helping out. I do appreciate that. How's the font size? Do you need me to increase the size? Is it legible? Everybody, you can put a yes or no chat window. Okay, it's okay. It's okay. It's very fun. What if I do that? Is that better? Fahim, you said it's okay. Julio, you suggest that. Okay, you're telling me perfect now. Julio, hey, this is an interactive webinar for sure. Okay, so let's go ahead and walk through some code. Somebody asked about a dam. I made a comment around a dam being adaptive based on the degree of noise in the air. I'll leave it like that for the purpose of this webinar. I find it really interesting though, because it does keep kind of a running tab on the variation. So it does use kind of a memory, which I think is fantastic. I think it's really interesting. We'll use that methodology here. Okay, here's the workflow. All of the workflows are available on the learning management system. Avi gave his contact information. You can contact him to find out about signing up. If you're not already signed up for the learning management system, everything's available there, including recorded lectures too. So I think you'll have everything you need to kind of get started. Okay, we like to be with our workflows, we provide a lot of information. Anybody here, show of hands, has never worked with Jupyter Notebooks? Anyone? Anybody never used Jupyter Notebooks before? Okay, Corinne, I appreciate that. Thank you very much for the hands. Let me just make a general comment if everyone else doesn't mind. If you look at it, it's a bunch of cells. If I click there, there's a cell, and I click there, that's a cell. If I double click there, you'll see it's written in Markdown with links and formatting and enumeration and so forth, and subheadings. If you hit run, you can build really beautiful documentation. This is a Jupyter notebook right here. You've got the cells, you build your documentation. Then you have a sequence of blocks. Here's some code right here. We're going to import some packages. This is the geostat.py package that I coded up. I think I used some visualization from it, that's all. We're going to import NumPy, pandas, Matplotlib. These are kind of standard packages people use in Python for working with arrays, data tables, and data visualization. Now what we'll do, this is the big part right here. We're going to go ahead and import TensorFlow. Now, if you look really carefully, you're going to look at this code and you're going to realize that, in fact, I'm using a GPU configuration. I have my home computer has an RTX 2080 kind of an okay graphics card. I have to admit, I play games sometimes, okay, but I also do science, right? So I have a good GPU. Now what I've done is I've configured this whole thing so that when I run this environment, TF GPU environment, I'm now using my GPU. How do I know I'm running my GPU? Well, let's go ahead and import TensorFlow. Now, this code has been tested and will work if you don't have a GPU available. It's going to be run on the cloud if you work through our learning management system. And so have everything ready for yourself. When you run this code, it confirms, in fact, that I do have a GPU unit 0 available and I'm running it right now. Now we're going to go ahead and load a data set. Our data set, we can go ahead and look at the data table. It's depth versus normalized porosity. Super simple. I think it's going to be porosity with a mean of 0, variance of 1 or something like that. Let's take a look at it. Here's the data table right here. We'll go ahead and we'll ensure that we have min-max normalization of the depth and the porosity. Why do we have to do that? Because we want to work with min-max normalized for good activation function performance, centered on 0, minimum -1, maximum of 1. We're going to check to make sure we've done that correctly. You run that code right there, and you'll notice that we can see the min and max of my new features are -1, +1. So it worked. I have this ready to go. Let's go ahead and do a train test split. I'm going to say 35% test. That's pretty aggressive, but I don't have a lot of data. I want to get a good testing assessment. Okay. I really, if I use smaller, it doesn't work too well. Let's go ahead and visualize the data. Okay. You can see the original data, normalized porosity versus depth right here in Z in meters. You can see the train test split shown right here. Blue circles are test. Pinks are train, and you can see normalized porosity from -1 to 1, normalized depth from -1 to 1. This is what we're going to model with, but we'll back transform to get it back to the original space when we're done with our porosity estimates. Now what we can do is we'll specify where we want to predict. The answer is everywhere. We'll just set up a bunch of values from -1 to +1, where we're going to be making our predictions, and then we're going to build a simple artificial neural net. Anybody here not used TensorFlow before with artificial neural nets? Anyone? Renato, never used it. Okay. Amir, I see that. Mohammed, thank you very much. Dolora, thank you very much. Everybody gets full marks for just Keras. And Julio, we're going to use Keras here today. A fortunate thing about the recent update of TensorFlow is that Keras is built in as a module now. It makes it very simple. I have to admit, I would say I'd focus on just Keras too. If anybody's wondering, Keras is the front end, which allows you to build neural nets using kind of very simple functionality and classes. For instance, if we want to do a simple feed-forward, fully connected neural network, we can use the sequential command right here from Keras, and we just have to specify the first layer has one node. It's dense, meaning it's fully connected. Activation function is linear. We don't want to apply activation function. That's identity function. And the input shape is just going to be 1. Then what we're going to have is we have 2 nodes in the hidden layer. So imagine that, 1 node, 2 nodes. And then the output is going to be 1 node linear because we're making a continuous prediction. Our response is a continuous, that's a regression model. So that's a good question. If in general, we use a linear activation function for the input. Because if you think about it, the input is just going to be the transformed feature coming in. And so we really start applying activation functions in the hidden layer when we start to have linear combination of all the outputs from the nodes of the previous layer plus a bias term. Now apply activation to that. That's typically what we do. An activation to the input feature itself wouldn't really add any advantage. Okay, I hope that helps right there. All right. All right, because remember, activation is being applied at every node to prevent collapse of the system. Okay. Yeah, and so this is a really good question about the specific transformations we should use. -1 to +1 or 0 through -1. I agree that we could be more careful about exactly pairing what activation function with what type of a transformation we use. Here you're right. I've been a little bit sloppy. I should probably use a tanh, or I could change my transformation to be 0 to -1. I appreciate that. Very good point. Okay, so let's go ahead and we'll apply the DAM optimizer. I'm not going to get into, besides I'll mention this is learning rate right here. These right here are scheduled, are based on the degree of how adaptive this is over time as you're making the predictions, and how does it adapt to the kind of the history of variance in the testing, or the error. And we can go ahead and compile it. We'll put together our model with our optimizer. We'll specify the metrics that we're going to use. In other words, the loss function, mean squared error, L2 loss. And then we'll go ahead and we can fit with all of our training data. The validation data is our withheld testing data right here. We're going to make predictions over a bunch of different depth values so we can plot and see what our model looks like. Okay, so remember, we had only 2 hidden layer nodes. Does anyone have a prediction of what our model is going to look like? Look at that. Can you see it? Does everybody see what happened here? The ReLU function, I picked it because it had these nice, to be honest, I wanted this visualization. You see how you can see a ReLU function and a ReLU function. This is really the additivity of 2 ReLU functions, right? Being combined together. And so that's all we could expect to be able to reproduce if we have only 2 nodes. It's a very simple system. Now, how's it doing? How's it training? Well, look at the multiple epochs. We do 200 epochs here. We could do less and run it faster. And you can see we don't really improve the testing error. The training error gets a little better, but it's really not a great model. Let's go ahead and add complexity. Let's add 50 nodes to the hidden layer. Now we have a system that 1 nodes, 50 nodes, 1 node in the output. We can rerun that. That's going to take a little bit of time. Working with GPUs has a little bit of just transferring information, adds overhead to GPUs. And so it does take a little bit of time just to get started. Can we all see what happened? This is 50 nodes. This is our fit now. Are we improving? Is it a non-linear model? Well, certainly is it a non-linear model. Let's go ahead and look at how we trained. How did the training perform? Testing error, training error. Remember, we don't have a lot of data. It's a small problem. I'm not too worried about which is higher or lower. It's just probably kind of based on what exact testing and training split we did. But in general, you can see that the training is decreasing over epochs. The testing is also decreasing as we go along systematically. We might be able to train even a little bit longer on this. Okay, so now what happens if we add layers? What if we go to deep learning? How do we do deep learning? Well, now we have 1 node, 50 nodes, 50 nodes, 1 node. That is deep learning. That's a fully connected system. Okay, and so let's go ahead and run that. Now I agreed sigmoid would also be a good, so Ali Reza, I do appreciate the comment. Sigmoid would be a good choice for activation function that we could consider too. I appreciate that very much. The maximum number of nodes in each hidden layer. Now, this is very interesting. The actual paper that I referred to with the universal function approximator statement, it states that you can reproduce any function, nonlinear complicated, if you have sufficient width, in other words, number of nodes in a single hidden layer. Okay, so that is based on that result is based on the idea of width or number of nodes. I would agree that this decision is the hyperparameter that constrains very much the degree of complexity, number of parameters, flexibility of the model. And so I would say, Julio, that it comes down to it's like a hyperparameter we tune based on the complexity of the problem and our ability to generalize, right, to other cases that are not used in training, right? I hope that's helpful. All right, so we've shown a couple of examples here, kind of a very fast overview of an example. Julio, thank you for that. I appreciate the question. That was a very thoughtful question. Ali Reza, I do appreciate that too. So we've shown some examples now. There's other demonstrations available. And of course, there's other topics like convolutional neural nets. I would also suggest that if you're not familiar, please step back and go back and review probability, review optimization, review fundamentals like variance and bias trade-off. I do think when it comes to using these types of models, we need to kind of understand the basics to ensure good utilization. I do appreciate the comments about sigmoid. That was great. Great catch on the transformation too. I do appreciate that. Very fun. I'll tell you what, I'll hang out. I like simulating the real world, like as if I'm in person. I never give a talk or a lecture or anything and just run out the door. I hang out for a bit. If anybody has any questions, I'm happy to discuss. Otherwise, thank you for joining us, even though we made it difficult to join today by changing the date, locking the registration until this morning. Oh my gosh. Thank you very much for your tenacity in joining today. All right, see you all. Stay safe. Yeah, Newsrat, thank you very much for that question. Now, we can say that the method we demonstrate today and the general method used for artificial neural net training is a form of coupled backpropagation and stochastic gradient descent. Okay, that's the way I would describe it, right? And now the reason we call it stochastic is because when you do the batches, it means that you're going to have a random, and somebody said bootstrap, and I think that's a great way to think about it. You're basically bootstrapping the error, and then you're back propagating that through. That causes stochasticity in the actual updates of the weights. Now, there's tons of good reason that we don't do just regular gradient descent and we go to stochastic gradient descent. It's just more robust. It's been shown to be faster and work in more problems. And so the batch approach introduces stochasticity, and the updating of the weights is a stochastic gradient descent. And it's coupled with backpropagation so we can keep calculating the gradients at each one of the parameters so we know how to update. Okay, I hope, Nusrat, I hope that's helpful to you. Renato, do we have a geostatistician in the room? I have a sense you're asking me about sequential simulation, Gaussian simulation. The fact that you said direct simulation tells me that you have some deeper geostatistical knowledge. I'm curious, if you're a PhD student or a former graduate from one of the geostat centers, please let me know and I'll say howdy. Very cool. I came from the Alberta group working with Deutsch. So let me make a general comment about machine learning versus geostatistics. And I think this is fascinating. First of all, we in our research group with my 15 PhD students have been finding ways that we could use machine learning. I hate to say it, but instead of methods like sequential Gaussian simulation in order to get very good realizations of the subsurface. Okay, so let me make that as a first comment. There are opportunities to use machine learning to do geostatistical type of operations, but we got to be very careful. We got to remember our roots, and we got to remember where we came from, and that was data conditioning, reproduction of global statistics, reproduction of trends and secondary information, spatial continuity, and so forth. It's very important that we get those aspects in, and finally, we represent it through ensembles that represent uncertainty or sample uncertainty, I should say. Those are all very, very critical. Okay, so when we do this with machine learning, we're very, very careful to do that. Okay, now, if you think about it, if you are kind of wanting to form more linkages, consider this. Clayton Deutsch's PhD thesis was all on how to do simulated annealing in order to solve for multiple point simulation and other types of data or information integration into subsurface models. So the idea of using an optimization method, which is trying to estimate to build ensembles like simulated annealing, that has also been something done before. So you are right, Renato, I agree with you when you're thinking that there are linkages between geostatistics, optimization, machine learning methodologies. There's so many linkages and connections. I hope that's helpful. All right, all right. Hey, thank you for letting me know. I appreciate that. Okay, if there's no further questions, I'll take off. You know, it's amazing. Summertime is here and my students and research, there's always something. Greetings from CCG. You're doing the masters. Abdel Kiram. I'll have trouble with your name. I do apologize for that. I'm going to unmute you. Do you want to unmute? Let me see that. Are you able to talk?
Yeah, sure. Hi, Professor.
Oh, Fabio, you're also okay. You're getting unmuted. Okay,
Yeah.
Are you able to talk? Am I hearing you?
Okay, now you put me in a tough spot here.
I can hear you. Okay, both are you from CCG up in Alberta?
Yeah.
Fantastic. Okay.
Yeah, I'm working with Professor Deutsch. Yeah.
Okay. Okay. So you're with. Okay. So was that Fabio?
Yep.
Yep, and I'm with Dr. Jeff.
De Boivort, right?
Yes, right.
Boivort. Oh,
Yes.
very good. Please, greetings to Jeff and Clayton, good friends of mine. Of course, you know, academically, that makes us siblings. Well, siblings, and one of you is a nephew because I studied with Deutsch, and so did Dr. Boivort. So I was one of Clayton Deutsch's early students before I went to industry and then moved down to University of Texas at Austin. So just a pleasure. How's everything up in Alberta?
Well, thanks for that, Doctor. And everything's good. We are struggling with the heat wave here, but yeah, everything
Now,
good.
I heard about that. So,
Yeah.
you know, usually it's us in Texas who struggle, but I guess you have a heat wave and in Alberta, you don't always have air conditioning, do you?
Yes, right.
No.
My wife and I remember we were in student housing and we had a really hot summer and we were in Michener Park actually for a while when we had kids in our PhD.
Oh,
Okay.
yeah.
Awesome. Well, just a pleasure to hear from you guys. If you don't mind saying howdy to Dr. Boivort and Dr. Deutsch, a pleasure to have you here. Thank you for joining in, and sorry to put you on the spot. Just have to say howdy to Albertans, right?
Yeah,
Thank
sure.
you.
No problem, Professor. I'll tell them, and thanks for your lecture. It was very good, very clear. Hello.
Okay, everyone stay safe. Let me just ask before we bail here, is there anybody else with a question or comment? Anybody else suffering from the heat wave in northern North America? No. All right, okay. Oh, somebody else. Nusrat, where are you at? May I ask? Calgary. Oh boy. Yeah, I'm sure you're in the same boat, eh? And okay, and Delora, you're in Africa. Very cool. May I ask what part of Africa? Cameroon, very cool. Gaia, I probably got that wrong. I apologize. Botswana, very cool. Okay, I did spend about 2 years in a little over 2 years in Tanzania. Actually, my second language is Swahili. I loved East Africa, but I know, of course, Botswana is a way away. But that's very cool. We got a couple from Botswana, maybe from the same group or company or school. I love it. I'll tell you what, my goal in sharing all my university content is to invite everyone off campus to be able to learn together. And I just am stoked to see people from around the world. Thank you very much for letting me know, folks. I appreciate that. Okay, all right. This is too much fun. I better go and take off. I need to get ready for some stuff. And we have Ecuador, Julio in Ecuador. Very cool. Very nice. Thank you very much. I appreciate everybody for joining. All right, I'm going to take off. Stay safe, everyone.